So I'm going to be talking about random coxeter groups. So I'm actually going to start off by telling you about random right-angled coxeter groups specifically and how that all works, and then I'm going to shift over into talking about random general coxeter groups, which is what my research is on. So I'll start off by telling you what a right-angled coxeter group is. So definition, I'm going to let gamma be a finite graph. Then the right-angled coxeter group associated to gamma is just given by, so first of all, we're going to call it W sub gamma, and the generators of this group are just going to be the vertices of this graph. So vertices vi of the graph gamma. And then for the relations, we've got two things going on. So first of all, every generator squared is going to be 1. And second of all, two generators are going to commute. So we've got vi vj equal to vj vi, exactly when there's an edge between vi and vj in the graph gamma. Okay. So when I talk about random right-angled coxeter groups, really what I'm doing is I'm taking a random graph, and then I'm looking at the right-angled coxeter group associated to that graph. So let me write that down. So a random right-angled coxeter group, that's how I'm going to abbreviate that, is just the coxeter group, or the right-angled coxeter group associated to a random graph. Okay, so I'd better tell you a little bit about what a random graph is. So typically when people talk about random graphs, we're talking about the Erdős-Rényi model. So Erdős, I think that's the way that goes. So the Erdős-Rényi model for random graphs. So there's a couple different things this could refer to, but what I'm talking about is I'm going to let p of n. So p is going to be sort of the probability of an edge happening. It depends on n, so it's, I guess, a function from natural numbers to the interval from 0 to 1. And then I'm going to say the random graph gamma of n and p. So it has n vertices. So n here is the number of vertices. So it has n vertices. And I'm going to look at each edge that could possibly be in this graph on n vertices, and I'm going to say that it's there with probability p. And each edge is chosen independently with probability p of n. Okay, and then generally the idea is like, so we have this like random graph on n vertices with our function, or the probability function that depends on the number of vertices, and then we look at what happens as we let n go to infinity. So let me just write this down mostly so I can use the abbreviation. We'll say a random graph asymptotically almost surely has okay, the whole point of this is so I can use this abbreviation. I'm going to just write that as AAS for the rest of this talk, because that is a lot fewer letters than the entire thing. So it asymptotically almost surely has some property that we care about. It's a property P. If the probability that the random graph on n vertices with probability P has that property goes to 1 as n goes to infinity. All right, so we're talking about things that are happening as the graph is getting really big.
Your property is a function, not just a number, right?
So yeah, the probability is a function depending on n. So typically what's going to happen is the probability function is going to drop off as n gets really big. So you're having, you're getting a lot more edges that could or couldn't be there because there are more vertices, so there are more edges to be had. And so like if you don't drop off your probability, you just get a lot of edges, and for depending on what you're looking at, that like usually you want like at least some of the probabilities to be dropping off. Or this is only so this is only one probability. Slight preview onto the general coxeter group case. Okay, so the general like to study random right-angled coxeter groups. Like the general procedure for doing this is, first of all, you identify some interesting property you want to know about when a random right-angled coxeter group has that property. So identify a property P identify an interesting property when you care about that a right-angled coxeter group W gamma might or might not have. And then, so step 2 in this process is you're like, okay, well, I've got this property of my group, but I really and I know how to look at random graphs and see what's going on in the random graph. But I'm going to want to show that W gamma has this property P, if and only if the graph gamma has some property Q. So I want to figure out how to see this property that I care about in the graph, because that's how I'm going to be able to do anything. And then part 3 is to find conditions on the probability function P of n, so that the graph gamma asymptotically almost surely has the property Q. And so the reason I'm breaking it down like this is just to make it clear that there sort of are 2 separate parts to doing every any problem that you might want to do for these random groups. Okay. Any questions so far before I get into specific examples?
So what's the difference between a random coxeter group and a random right-angled Artin group? Or perhaps I should say a coxeter group.
Yeah. So you can do this whole thing for right-angled Artin groups too.
So what are they? They just don't have. Is it that they just don't have the VI squared?
Yeah. So if I was talking about right-angled Artin groups, just this first condition would have been left off. So
I see. And coxeter means that you're thinking of these things as reflections. That's
Yeah.
how you put that in.
Yeah.
Right.
Yeah. Any other questions? All right. Okay, so what are some cool properties that right-angled coxeter groups might or might not have? Well, oops, I got a little bit ahead of myself and left my second page behind. So one example is hypervelicity. So this is the same, delta hyperbolic thing that like people have been talking about all week. So I'm not going to define it again. But sometimes right angle coxeter groups are hyperbolic and sometimes they're not. And it'd be cool to know like when a random right angle coxeter group was or it wasn't. So helpful fact, which this is like basically a special case of the theorem of Musang, which I'm gonna give you the full theorem in a little bit, but for now I'm just gonna give you the right angle coxeter group case. So a right angled coxeter group is hyperbolic if and only if the graph gamma is square free. Actually, I think we've seen this talk before. I don't remember. Maybe it was Kash's talk. So this just means your graph can't have an empty square like this where these edges are missing, and then it's always hyperbolic. So all right. So this is so far we've identified hypervelocity as a property that we might want to have, and Musang has helpfully showed that that's equivalent to this property in the graph. So then from there, it's a theorem of Ruth Charney and Michael Farber. The sort of the random part of this is their theorem. So if NP goes to 0, then W gamma is asymptotically almost surely hyperbolic. And if NP goes to infinity and 1 minus p times n squared goes to infinity, W gamma is asymptotically almost surely not hyperbolic. Oh, and actually I left this out in my notes, but if this goes to 0, so if NP goes to 0, or if 1 minus p times n squared goes to 0, so if this goes to 0, then it's just finite, and so it's like hyperbolic, but that's dumb. Okay. So this is sort of nice. This is like as good of a result as you could hope for, because you got like, if like these two things both go to infinity, then like we know it's not hyperbolic, and if either of them goes to 0, then like we know that it asymptotically almost surely is hyperbolic. So this is a very nice theorem. My theorems are not going to be this nice, and so we'll see why. I mean, part of it is because I'm like not as smart as these people, but like, but also it's more complicated. Yeah. So are you? It leaves the case where those things go to something that's between 0 and infinity. Yeah. That's like that's like not something you could hope to. Yeah. So it's not like a totally exhaustive like list of all the possible cases, but like. Yeah, this is like a threshold function. Other questions? Okay, so something similar. Well, I'm not going to write down that statement, but just something similar to this can be done for general coxeter groups via edge-labeled random graphs. So let me first of all define a general coxeter group and then get into that. So we're going to let gamma be a finite graph again. But this time, each of the edges is going to be labeled with some label picked from integers at least 2. And sometimes this is going to come up. So if an edge doesn't appear, we'll say it's labeled infinity. Just like sometimes I'm going to refer to that. So I will and sometimes refer to edges not being in the graph, and sometimes refer to edges being labeled infinity, and those mean the same thing. So then the coxeter group associated to gamma this time is, so again, we're going to have, so still going to call it W gamma. Again, the generators are going to be the vertices. And, well, again, we're still going to have vi squared equals 1 for every generator. But now we're going to have vi vj to the m equals 1 if, so if the edge between vi and vj is labeled m. Okay, so going back to the right-angled coxeter group case, if you're more familiar with that, an edge in the right-angled coxeter group graph is the same as an edge labeled 2 in the general coxeter group graph, because that's like, you get like vi vj equals 1, and vi and vj are their own inverses. Okay, so, and again, random coxeter group, we're going to talk about picking a random labeled graph, a random edge labeled graph, and then looking at the coxeter group associated to that. So, so for the random edge labeled graphs, basically, it's just an extension of the Erdős-Rényi model. So, I don't know. I'll call this the extended Erdős-Rényi model for edge labeled graphs. All right, so now this time, instead of just having one probability function that depends on n, we're going to have a probability function for every m that depends on n. So for each possible label m, 2, 3, 4, etc., we'll let p sub m of n go from natural numbers to integral from 0 to 1. And so we can't just pick any old probability function this time. We have to make sure that they add up to less than 1. So the sum from m equals 2 to infinity of p sub m of n has to be less than or equal to 1 for every n. And that's just because we're only, well, let me write down. So the random graph and this time I'm going to call it gamma of n, and then I'm going to tag it with the sequence of all of the PMs. Again, has n vertices, and each edge is labeled so independently of like the other edges. Independently of other edges. So wait, hold on, what have I written? So has n vertices and each edge is labeled independently of other edges. So it's labeled, labeled m with probability p sub m of n. Okay, and just the reason I'm being a little bit careful about saying it's independent of the other edges is because obviously the probability that an edge is labeled 2 is not independent of the probability that it's labeled 3, because those can't both happen. There's only one label on each edge. But the edges, or the labels, are chosen independently for the edges. Okay. Questions about this? Yeah.
In
Oh yeah. So if you didn't pick a label, so the probabilities add up to less than 1, or yeah, less than or equal to 1. If you didn't pick any label, then there's an edge labeled infinity or like a non-edge.
Okay.
Other questions? Okay. So just like we talked about hyperbolicity for writing on coxeter groups, we can talk about hyperbolicity in general coxeter groups. So again, hyperbolicity. So this time I'm going to state the full theorem of Moissan. So a coxeter group with generating set S is hyperbolic if and only if the following hold. So there's two conditions. One is we can't have any, so there's no subset T of S, which generates an affine coxeter group with at least 3 vertices. So that means we can't have any of these guys, except this one is OK because it only has 2 vertices. But any of these other guys we can't have, or else it's not hyperbolic. And then, oh, well, that's OK. My like dramatic reveal is about to like. Oh yes, thank you. Okay, I should like tell you what these pictures mean. So in these pictures, the unlabeled edges are 3s, and the edges that aren't shown are 2s. So if there's not an edge, it is actually labeled infinity. If there doesn't appear to be an edge in the picture, that means it's labeled 2. Questions? Thank you for reminding me to tell people about that. I always forget. All right, so the other thing that has to be true for it to be hyperbolic is there are no disjoint, two disjoint subsets of the generators such that both T1 and T2 generate infinite subgroups, and they commute. So sadly, I'm going to bring this back in a second, but these are the like finite. These and like direct products of these are the finite coxeter groups. And so if you have like 2 things that are not on this list, and all of the edges between your 2 separate things are 2s, then that's bad and you're not hyperbolic. So sorry, I'm going to hide this again so you can see.
Can you say again what these pictures mean? Because I'm so used to thinking of these as root diagrams or something.
Okay, yeah.
And they're rather different as well.
So the vertices are still the generators of the group. The edges that are shown that are not labeled in the picture are actually labeled 3. If it has a label, then that's like the label that it is. If an edge is not in the diagram, then there is an edge and it's labeled 2. And that's just done because there are so many edges labeled 2 that like the picture would be unreadable, right?
So that just means that they commute.
Yes. Yeah. If there's
commute if there's no edge.
Right.
And otherwise, typically, they're labeled 3.
Yeah.
Okay.
Other questions?
But these are the Dinkin diagrams.
Well, those are the Dinkin diagrams. These are like, sorry.
Well, the ones
These are the Dinkin diagrams.
No, but for an affine coxeter, I mean.
Oh, are those also considered Dinkin diagrams? I don't. Yeah. Sorry, I thought the Dinkin diagrams were just the finite ones, but that like could totally be false. Other questions?
What about the classical ones for the classical Lie groups?
Yeah, I don't know very much about Lie groups, but yeah, Dinkin diagrams classify a lot of things. So if you think you've seen these before, you're probably right. Other questions? Okay. But anyway, so the point of this is we've taken this like condition of hyperbolicity that we're interested in, and we can see both of these conditions in the graph. So now we can do some like random stuff and figure out when when the group is or isn't going to be hyperbolic. So all right, so this, I guess, is my theorem. So we're going to let gamma and then this sequence of probability functions be a random edge-labeled graph. So first of all, if n to the fourth p2 to the fourth p infinity squared goes to infinity, W gamma is asymptotically almost surely not hyperbolic. And that's basically, so I'm not really going to give any proofs here, but that's basically because you get, you get like two infinity labeled edges that commute. So that violates this second condition. And then if np3 goes to infinity, again, W gamma is asymptotically almost surely not hyperbolic. And this time that's because you get a triangle whose edges are all labeled with 3s. So that falls under this first thing over here, and these are also infinite. Okay, so, but then the third part, which is kind of the coolest, so if 2 goes to 0 and np3 goes to 0, then W gamma is asymptotically almost surely hyperbolic. Okay, so yeah, you can see it's not quite as clean as the proof for right-angled coxeter groups, but you almost I don't expect to see a threshold function for this because there's just a lot going on with the different probabilities of different labels, and that would be hard. Any questions about this?
So the P5, P6 never come up in your
so, I mean, they sort of come up. Those labels can be on the graph. It's just that whether it's hyperbolic or not doesn't it sort of doesn't depend on that, except in the sense that if you have more edges labeled 2s and 3s, then you necessarily have fewer edges labeled with other things, and so but yeah, it certainly doesn't matter specifically what the ratio of edges labeled 4 to edges labeled 6 is. Other questions?
Can I ask, so if it's not going to be hyperbolic, then what are the categories exactly? So are you saying then it's affine, or is there something else?
So when I say it's not hyperbolic, I mean it's not delta hyperbolic. So there is also there are also things called hyperbolic coxeter groups, and that's actually a different thing, and it's not equivalent, which is annoying. But I just mean that it's not delta hyperbolic. Does that answer your question? Kinda.
I guess. I mean, I don't know as much about, I basically only know affine coxeter groups.
Okay.
And finite coxeter groups, so I don't really know much about other categories, but I'm just wondering if this is the entire universe of everything that it could be, or are there some like positively curved things that it could also be, or like?
I don't think you're going to see anything positively curved, but like, yeah, I don't know. I mean, I know when it's delta hyperbolic and when it's not delta hyperbolic, and like, other questions? Okay, so that is one thing. I also have looked at some like other properties of random coxeter groups that are maybe a little bit more technical. So this like in some sense the like hypervelocity thing is sort of the flashy like thing that somebody might actually like, you know why you should care about it, but like it's also the thing that I had to do the least work to prove, because like Musang did all of the work of like getting it down to the graph thing, and then actually it, like the proof of like the random part was like not that hard. So the thing I've spent more time working on is this property called FC type. In, I guess, random coxeter groups. All right. So, and I am keeping an eye on the time. I promised some people I would be done by 12:15. So, I'm aware of that. So, first I'm just gonna tell you what this property is, and then I'll like, I don't know. I'll state the theorem and like maybe wave my hands out a little bit of like what some of the work that went into the proof was, but maybe not. So a coxeter group, W gamma is of FC type if every induced subgraph of gamma which does not contain an edge labeled infinity, corresponds to a finite subgroup. All right, so this is sort of like some kind of a finiteness condition, right? We're saying, okay, well maybe our group isn't finite, and maybe you know if you look at every induced subgraph, maybe the group you get from that isn't finite. But whenever it's not finite, we should have this edge labeled infinity there to like show us that it's like really not finite. Okay. Corresponds to a finite subgroup of the group. So maybe this would be a good time to bring back up the finite diagrams. Okay, so I'll at least write down my theorem. It's like kind of gross, but like so theorem. Oh, I guess I should point out. So this is like this sort of is really a property of the graph. So it, like that first part where we go from the property in the group to a graph property is like automatically done just by like what the property is. So yeah, so this is me again. We're going to let gamma be a random edge-labeled graph. And just like for notational reasons, I'm going to let p sub b be the sum from m equals 4 to infinity of p sub m. So I'm adding up all of the big numbers into like one thing, and because it's going to turn out that like again for this property it doesn't really matter whether you have like a 4 or a 6 or a like 28. So if any one of the following hold, W gamma is asymptotically almost surely of FC type. All right, so here's where it's going to get kind of gross because I'm still a little bit working out the kinks of like presentation of this. But so you could have n to the 5th, p3 to the 4th going to 0, and all of the big labels just can't happen. So PM is just 0 for all m bigger than 3. So in this case, our only labels are 2s, 3s, and infinities. You could also have nb3 going to 0 and p2 to the 6th just not going to infinity. And again, big labels can't happen. So PM is just 0 for all m greater than 3. Okay, but we want, like, sometimes we want to have like some big labels in there. We're not going to be able to have too many just because of like what the property is, but we want to be able to have some. So we'll say, so if n cubed pb squared goes to 0, and n cubed pb p3 goes to 0, and n to the 5th p3 to the 4th goes to 0. Also, it's going to be asymptotically almost surely of FC type, and oops. If n pb goes to 0, np2 does not go to infinity, and np3 goes to 0, then it's going to be asymptotically almost surely of FC type. So this is like half of the theorem, and then the other half, yeah, maybe I'll write that down first, and then I'll like maybe try to wave my hands at some of this if it's not too late by that point. So the other half of the theorem is when it's not FC type. So if any one of the following holds, then W gamma is asymptotically almost surely not of FC type. Okay, so this is a little bit simpler. So if np3 goes to infinity, it's not going to be of FC type. And again, this is because of the like, we're getting the same triangle that's labeled with 3s, and that's infinite but doesn't contain edge labeled infinity, so that's no good. Also, if npb, so if n times like, so pb is the sum of everything bigger than or equal to 4. So if that goes to infinity, it's not going to be FC type for basically the same reason, except our labels can be anything higher than 3, and that still is going to be infinite but not contain any infinity labeled edges. And the other possibility is that npb does not go to 0 and np2 goes to infinity. And basically the same thing. In this case, you're going to get, what are you going to get? You're going to get like, you're going to get a triangle with, you're going to have two big labels, and you're going to have, wait, is that right? Yeah, two big labels and then an edge label too. So this part's like maybe not super thrilling, but so I guess, yeah, so, and yeah, this is the like, this isn't even like all of the cases, these are just the like kind of nice ones. So like the probability part is like kind of involved and like and like slightly complicated, but basically sort of the like broad like thing here is like there's a couple of different like cases you can be in. Either you don't have big labels or you do. The other thing is either we're paying attention to what's going on with the two labeled edges in the second and the fourth option, or we're not in the first and the third option. And so basically you get like a little bit of a cleaner, well, in some ways cleaner thing if like you can have as many or as few two edges as you want really in cases 1 and 3. But then if you start thinking about what's going on with the two edges, you can tighten up some of this stuff. So this is like this is better than that. So yeah, I don't know if anybody has any like suggestions for how I can like present this information in a way that is not terrible. I would be happy to hear them. But yeah, and I think probably it's too late to do anything reasonable about waving my hands at a proof. So we'll not even try.
Let's thank Angelica.